So good afternoon, everybody, or good morning, depending where you are, or good evening, good late evening. So I would like first to thank the organizer to invite me and give me the opportunity to present my results, and especially that I'm not really biophysicist, so it's my pleasure to be here. So what I'm gonna talk about is really inspired by biology. And so how it's about active polymers and filaments in heterogeneous media. But just to clarify the terminology, what I mean by active polymers and filaments, I will give an introduction to them. And then I will move what is special about active polymers and how their scaling properties differ from passive polymer and filaments. And then I focus on my research, which has been done in my group about active polymers in ordered and disordered media. And finally, in more dynamic environments, which is like granular matter, which is a work in progress. So let me get started. So what do we mean by active polymers and filaments? If you look at nature in biological systems, you find a variety of systems which are filament-like. They are elongated. They also can bend and curve. You can find them in different length scales from micrometer in bacteria motor-driven biopolymers like actin and macrotubule in cell cytoskeleton. If you go to more macroscopic length scale, you can find worms and snakes, even larger scale. And what is common among all these systems is that, yeah, as I told, they are elongated and flexible. They are not stiff, like rigid like rods. But they are also self-propelled. They involve some sort of active process. And this has also inspired design of synthetic systems. Like here is the example of chain of a hex box, which is done by my colleagues in Amsterdam. And you can see they are really like a macroscopic realization of active filaments. And another example is this colloidal caterpillar, which seems today is not working, the video, but yeah, it's working. It has a bit of delay. As you can see, that it's just chain of colloids which are connected and they move like a caterpillar in a macrofluidic channel. And so these are the examples. And just to be more abstract, or just to clarify what I mean right now for active filaments, I think active filaments is not a new topic in a way. It just there is a resurgence of interest recently on it. And also I'm focused on a specific class of active filaments, which are self-propelled one. But of course, active filaments can be beyond just self-propelled. But for the purpose of today, by active filament, I mean any filament-like system which can be modeled in a coarse-grained view by a bead spring model or just a continuous filament, which has a active force profile along its backbone. So how can be the active force profile varies from one system to system or the model to another model. One of the very most common one which was put forward is the active Brownian polymers, which is nothing but a chain of Janus colloids, which each of them is doing active Brownian motion. Other examples include tangentially driven active polymers, which will be the focus of this talk. I will tell you more about it, where we assume that active force is tangential to the backbone. You can have a variety of possibilities. Another option is that the active force is perpendicular or any combination of them. So you can look at these references if you'd like to know more about it. And there has been a relatively recent review about active polymers and filaments in 2020 by Roland Winkler and Gerhard Gomper. Just why active polymers are interesting for me. For me, it's really an interdisciplinary topic. It's a playground that you combine in the first place active matter physics and polymer physics. Of course, it's biology inspired, so biophysics plays an important role. And as I told, it has also found inspired applications in robotics or broader than robotics, and there has been a lot of interest in soft robotics inspired by physics of active filaments. So the bigger question in the field is what new physics emerges from the coupling of internal degrees of freedom and activity, which can be local along the chain backbone. As I told, my main focus today is about active filaments in heterogeneous media, and the motivation of the work is again comes from biology, For example, if you look at the cell cytoskeleton, you have the actin filaments, which are driven by molecular motors, but there are also passive intermediate filaments and another other type of filaments. So you can look at think of active filaments moving in a heterogeneous medium. Another example, this filament like a parasite in blood flow, or worms in granular in soil, which is granular matter. And my colleagues in Amsterdam also are looking at the tube effects in a static area of obstacles that I will get back to it in the continuation of the talk. And also, you can find heterogeneous media, but that somehow the obstacles are ordered. Actually, you can also find in nature. For example, here I show the example of cicada's wing, and if you zoom in, it has really nice array of hexagons. And here is a big bacterium which moves on the top of these obstacles. And my colleagues in Amsterdam again look at the tubifex worm in the square lattice as well, like Oran disorder. And you can have also industrial applications. For example, they use the flow to separate worms of different type of activity, and the way they tuned the activity of worms was just to make them more drunk. And then they realized that actually they can separate drunk and sober worms, and this was so funny that they got an Ig Nobel Prize in chemistry this year about it, last year about it. So the key questions I'm gonna focus on today is based on the motivation I gave you, is actually how does the arrangement of fixed obstacles affects the conformation and dynamics of active polymers. Of course, the real heterogeneous media are much more complex, but just to keep things simple, let's start by a fixed array of obstacle 2D. It's very like circular because it's very simple, and we just look how it differs from ordered to disordered. And the next step, we can modify more. We still stick to 2D systems, but we just allow for obstacles to be able to be moved by the active filament, and that's an example of, for example, worm moving on the soil. So let's get started. And as I told you, there are variety of active polymer models. So the question is that what model we are choosing. We opt here for a model which I find very interesting, is this tangentially driven active polymer model, which was put forward by the group of Gerhard Gomper. And as I told, the feature of this model is that the active force is tangential to the backbone. And to me, it's a first order reasonable approximation for many biological systems. For example, the motor-driven biopolymers, when the motors and the motility assays, so the motors, when they propel the filaments, they exert tangential forces along the backbone of the polymer. Another example is the worm. If you look at it, at least the type of aquarium worm, at the first order approximation, it really moves along its backbone. And also the case of robot I showed you is by constraint. They have put a elastic shell along the robots that constrains the active force, the self-proportion, to be tangential to the backbone. And also from analytical point of view, this model has an advantage because the active force is tangential to the backbone, so it's like given by the sum of the bond vectors connecting to monomers. The total active force of the system is proportional to end-to-end vector. So if you want to look at the active force dynamic, it's enough just to look at the end-to-end vector. So it was helping us at least to obtain analytically the center of mass dynamics of this model in an easy fashion. So this will be the focus of this talk from now on. And just to motivate you before I go to my results of my our simulations, let me show you an example of this tubifex worm in the square array. We start from the ordered, which we think is a bit easier. So the worm is unfortunately a bit small, but you can see that sort of the worm at the first look looks like moving along its backbone, but of course it curves around the obstacles, and you can see that there are sometimes that it's getting trapped. There are moments that it just goes more straight. So keep this in mind when I'm going to continue to discuss with you the results of simulations and the experiments that we have compared our simulation results with the experiments on worms. Sorry, I stop. Okay. And then no, I went to the wrong text for some reason. I start again. Sorry.
No worries.
Yeah. So now you are seeing again my screen. So I skipped the video. So I go directly to the baby simulate these active filaments in periodic arrays. So basically the setting is quite simple. We do a bidex spring model in the overdamp limit. And we apply this tangential active force rule. And of course, you allow for some noise. The noise can have biological origin or thermal origin. It's very generic, the formalism. And we focus on size of obstacle, which are like about 10 times bigger than the size of the monomers. And the reason is because motivated by the experiments of our worms on these pillars. So that explains why we chose this size ratio. And uh, these worms are really 3D, but when we look at them under microscope, we see a 2D projection. And they are quasi 2D because first sediment because of their weight, but also because of the 2D projection, we see only 2D, but the result is that they can cross each other. So that's why we use a 2D ideal active polymer model or phantom model. That means that we don't consider self-avoiding work. We just allow the polymer to, it can cross itself because of this 2D projection effect. Also, in reality, it doesn't. And we allow the obstacle, the interaction with the obstacle are just excluded volume. That means that the worm or the active polymer cannot cross the obstacle. So it's very simple model. And just before I go, because maybe the audience are quite broad, I would say that we consider there are two key parameters for active polymer model in free space. One is the bending potential, which determines how easily you can uh, bend your filament. So it's given by this bending modulus kappa, which you can show that in 2D in equilibrium. The persistent length is given by ratio of kappa to kbt. And so the degree of flexibility can be defined as the ratio of the polymer contour length to the persistent length. And the other important parameter, key parameter of the model is the strength of active force. And as I told here, is the active force is tangential to the backbone, but is somehow coupled to the conformation. So there is a feedback loop how the polymer behaves depending on how the conformation is. The total active force changes, which is proportional to the end-to-end distance. So just to give you an intuition before I go and show the behavior of polymers in the confined environment of porous media, let me show you their behavior in the free space. So I show you two cases. One is flexible, which is kappa equal 1 is fully flexible. And the other case is very stiff one. And as you can see, when it's very flexible, you get a coil-like conformation. And it's quite compact because especially it can cross itself. On the other hand, for the case of the semi-flexible polymer, you can see that it's just more elongated. It has some transverse fluctuation, but overall, because of this railway-like motion of tangential, it goes quite straight with some fluctuations. And I would like to give you an intermezzo of what is the scaling behavior of active polymers, what changes when you switch on activity compared to the passive polymers. So in passive polymers, if you are familiar, we look at typically a static scaling, which is the scaling of end-to-end distance with the chain length. And typically, we know that it goes n to the power of 2 nu. There is something, a prefactor called Flory's constancy infinity, which is a function of the bending stiffness or persistent length. And this new value depends on the dimension, the fact that polymer is self-avoiding or is ideal. And for ideal, you have the value of 1/2. And as I'm right now, I focus on the ideal chain, so I just cite this value. And then you look at the dynamic scaling. One is look at the orientational end correlation function of end-to-end vector, which is you look at the end-to-end vector, you take the unit vector of it, and you calculate its correlation. Typically, it decays exponentially with a relaxation time, which is scaled as n to the power of 2 nu plus 1. So for ideal chain, it's simply n to the power of 2. So, and the other important dynamical parameter is the center of mass diffusion, which scales as 1 over n. So that means the larger the polymer is, the slower the polymer diffuses, which makes sense. And as you can see, this rotational relaxation time also is proportional to what is called Rouse mode. Rouse relaxation time is even for this simple case is going scaling quite large with n because it's n to the power of 2 in the best case, and for self-avoiding is even bigger. And what happens now if you make the polymer active? One thing that changes, I'm not going to go into detail, is that this stiffness constant, Flory's constant, not only depends on the bending stiffness, but also can depend on active force. Also, the scaling exponent can deviate from the passive case, and it can have dependence on active force. This is impressive for the case of self-avoiding walk, because you can see that it goes from 0.58 in 3D to the half, which is for ideal chain, simply because of activity. But what is most impressive is the dynamic scaling, because the rotational relaxation time now is scaled as proportional to n. So this is known from the computation and some analytics, that means that the polymer dynamic becomes faster, and that's why we want activity. And this is, of course, valid for a range of activity. Activity should be sufficiently large, but not so large. For example, in dimensionless, active force is just larger than 0.01. But this accelerates a lot the polymer dynamics if you have a very long polymer, because of this railway-like motion of the active tangentially polymer. And if you look at the center of mass diffusion, you have, of course, a passive contribution, the same way you would have it for active Brownian particle. But then you have an active contribution that we have shown is just by summing over the dynamics of every individual monomer, that it's proportional to Fa squared, end-to-end distance squared, some prefactors which are constant, okay, divided by n squared, and the orientational relaxation time. But in the case of ideal chain, end-to-end distance is just going n to the power of n. And I think I have made a mistake, because there should be n. But what I want to say that I think I have one and two extra. But at the end, what you will find here is that actually ideal chain case, the active center of mass is proportional to active force and not dependent on n. No, actually, I haven't made any mistake, because tau n has also one n dependence. So at the end, you will get the n squared cancelled by n squared, and you get an active contribution, which is roughly independent of n, even for self-avoiding bugs. And that's what we have confirmed by simulation. Group of Gomper and Winkler have shown it by analytics. So it's quite impressive that you get a really active contribution, which just goes linearly with active force and not depending on the chain length, which means it can exploit a lot the transport of polymers. So this is in the free space. And as I told, the take-home message here is that activity influences dynamics profoundly because of this railway-like motion. So the question is now, what happens to these properties? I'm not going to look at the scaling, but I'm going to look at the dynamics when you have an ordered array. So we look at first at the rather low packing fraction of a square lattice of obstacles, circular obstacles. And again, for two kind of stiffness, one is a flexible one which is semi-flexible. So here I show you the flexible case. And you can see that the polymer moves, it's almost in the free space, because the void space between the obstacle is quite big. So occasionally it might collide with the obstacle and turns, but it's not so different from the free space. The same holds here, because there is enough spacing between the obstacles. It's not dramatically affected the motion and also the conformation by the obstacles. Occasionally it just goes around the obstacles. But what is impressive, if you go to sufficiently dense array of obstacles, which I show here, uh, so here is when interesting events happen. So I start with the case of actually my video is started with the semi-flexible one, but you can look at the flexible one first. And what you can, sorry, I need to start it. Okay, maybe I need to go with semi-flexible because the video goes this way. So with the semi-flexible one, something interesting happens because the channels between the obstacles are so narrow, it forces the polymer to go almost straight and occasionally make U-turns. So basically, what happens is that you get induce a unidirectional motion and occasional changing of the channel and going to a perpendicular channel because of the symmetry of the lattice. On the other hand, if you look at the flexible one, because these are like phantom chain, they get crumpled in between the pores, and occasionally they just open up and then go to another pore and they get trapped or caged, and then again they spend some time there, and then they again open up and go to another one. So in this case, you need to wait some time. Now you see that, okay, it's opening up just to pass through the narrow channel and go to get trapped to another channel. By the way, I forgot to tell, I know sometimes I speak fast, so feel free to interrupt me if you have any questions, because then it's easier if something is not clear. But I think I stopped the video because you see the phenomenology basically being trapped in the pores, like here, and then opening up and then going to another channel. And if you look at the time dependence of the end-to-end distance, you can see for the case of flexible case that when it's trapped in cage in between the pores, it has a rather a small end-to-end distance, but occasionally it just goes beyond some value, and that's when it hops, it gets elongated. But this is for a low active force, 0.1, so it's most of the time being caged or trapped, and occasionally it opens. If you increase the active force, you can see that the active polymer spends more time um, being spends a bit more time in the hopping state as well. So you have roughly equal amount of time being caged or being doing the hopping state. And of course, you have a very active force. It spends a small amount of time in the pores, and then most of the time it's just hopping from one pore to another. So active force really helps to get out of the cages. And similar phenomenology for semi-flexible or stiff polymers that you can see here. If you have a low active force, most of the time it goes straight, but occasionally it changes channel. But if you increase the activity, it's more likely that it just switches channels because it has the energy to overcome the barriers and just overcome the bending stiffness and just bend and go to another channel. So we have looked at the statistics, but I don't want to bother you. You can find the dependence of the mean hopping time and trapping times on the active force, which clearly the hopping time is increasing, reduces the mean time, the increasing activity. And the result of this is that it affects also the mean conformation because it's just given by this combination of these two effects, how much of the time is caged and how much of the time is hopping. And but we can see that at low active forces is mainly caged, so it's very much crumpled between the pores. So it has a very small active end-to-end distance compared to the free space. So in this curve, the blue circles are the free space, and the green ones are are under confinement. This 60% of obstacles. But as I told you, once you increase the activity, you increase the hopping, and then the conformation, the mean conformation approaches that of free space. Somehow you can overcome the barriers with activity. Likewise, for semi-flexible polymers, if you have a low active force, they get more elongated conformations. Because they do this unidirectional movement in the channels. So you get not much, but about 10% bigger conformations. But if you increase the activity, you can even make them more flexible than the in free space, and then you get even a smaller mean end-to-end distance. And if you look at the rotational relaxation time, in the flexible case, you have a smaller relaxation time, because when polymers get trapped in the cages, they just very quickly rotate. It was visible in the videos. And if you have high enough activity, you approach the case of the free polymers. And it's the other way around for the case of stiff polymers, because they are doing this unidirectional motion. So as a result of this, you have a much bigger orientational relaxation time at the low active forces. And if you have high enough, because of this frequent channel switching, the fact that they can become more flexible, you approach the limit of free space behavior. What happens now if you look at the long time diffusion, what I mean the center of mass long time diffusion? Here I have shown for both flexible and a stiff one. For the flexible one, so the blue lines are the free space, the green ones are the flexible, for the when they are under confinement with the periodic array of obstacles. So for the flexible one, you can see that at low active forces, the diffusion is slower. It's because most of the time it spends time in caging. But if you are high enough activity, as you saw, you almost recover the free space behavior. For a stiff, again, is in line with what we discussed, that a stiff polymers diffuse faster at the low active forces because of this unidirectional motion. And at high enough activities, you recover the free space movement. And we realize that the way you can predict the long time diffusion is very similar what we did in the free space, that again is proportional to the end-to-end distance and the orientational relaxation time, although they are changing compared to the free space. But what is important is that the way the porous media affects the end-to-end distance and the orientational relaxation time, the product of these quantities basically determine how the long time diffusion changes. And as I told you, at the high activities, both end-to-end distance and rotational diffusion were approaching the free space. That's why you would get the same as the free space behavior. While the shrinkage of polymer leads to the reduction of the long-time diffusion, but we had some, but depends also how rotational diffusion is reducing or increasing. But basically, the point that the combination of these two determines how long-time diffusion is changing. I'm emphasizing on this because at some point we want to compare our simulation results to worms, and they are a bit more complex, but still they seem to follow this trend. And so up to now, I have talked about ordered arrays. So now let's look at the disordered arrays, again, at the high packing fraction. So here I just show you some snapshot, again, for the very flexible and stiff polymers. So phenomenology looks a bit similar in the sense that you can see that the polymers can get trapped between the small pores, and then at some point they just do the hopping to go to get trapped in another small pore. Also for disordered, but the statistics varies, but I'm not going to go into detail. And if you compare the flexible polymers, the long time diffusion with in ordered and disordered media, what we find is that actually disorder helps the polymer to diffuse a bit faster at low activities. Again, at high activities, they recover the free space behavior, so it's not so interesting. But what is interesting is that at low activity levels, that we have a faster diffusion of center of mass compared to the ordered one. For the stiff polymer, it's the other way around. And what we can see that the disorder have a substantially slower diffusion compared to the ordered array. And the reason is because of this induction of the unidirectional motion in ordered array. Somehow the channels which are ordered, they guide the polymer. And as a result, they go much faster because they really go like a train in these channels. So this is the main difference, but otherwise they are quite similar. You have either reptation in channels or you just get trapped in between. Okay, you don't have trapping for the stiff polymer in ordered media because you just simply get channel switching because they are so ordered, but otherwise they are quite similar. And we have been also looking systematically how the obstacle packing fraction changes the both conformation and active diffusion contributions. As I forgot to emphasize that actually for the long-time diffusion, passive has not much contribution because it's 1 over n, and 1 over 100 is almost 0. So what you see is basically from the long-time diffusion is the active contribution. So if you look at here as a function of packing fraction for the very flexible one, you see the differences again appear at only high packing fractions. At low packing fractions, they are quite similar because polymer is not much hindered. But you see differences between when you make them more like a bit higher stiffness, like 10, you can see that the behavior can change because here the square lattice was much had a smaller conformation, but here it has a more extended conformation, the same at a higher stiffness. And if you look at the active diffusion, you can see that random packing, as you go to higher and higher packing fractions, has a lower diffusion for fully flexible. Only at the very high one, it can go over, top again, like the last slide. But it shows also some weird behavior in the intermediate stiffness because you can see that the periodic is a bit lower and the random is a bit higher diffusion. But again, if you go to very packing fraction, it just goes the other way around. But okay, for the very high stiffness, it's more clear that the orders are going diffusing faster. So I'm telling you all this, that is a bit complex. The only message I want to say, not to remember the trends, it's just that it's a complex interplay of activity and flexibility. It's because we are a bit struggling with this when we wanted to understand the data of warm. But nevertheless, what is important that you can understand the long-term diffusion in terms of the mean conformation and the time it takes to reorient the end-to-end vector. And now I move on to the experiments that have been done with my colleagues in Amsterdam, Rosa, who is a PhD student, and Antoine Deble. And I forgot to mention my PhD students, but these are the PhD students who have been helping with these projects. Mohammad, Tuan, and Rose, who has been a recent PhD student. And we wanted to see how good the tangentially driven polymer is for a description of worm. So one of the things we did, we look at the end-to-end distance unit vector correlation function. And what we find is that, so here the solid line is the experiments and worm, and the dashed line is the one of the simulations. They are not fully agreeing, but it's within the error bar, and they show roughly exponential behavior. So we thought it can work, and what we do is that just to compare experiments and simulation, we scale a time scale with the relaxation time of the free worms, the orientation and relaxation of the free worm, which I showed as tau e and 0 here. And then we look at the mean square displacements of the worms in both ordered and disordered media. So Rosa did the systematic experiments as a function of packing fraction in worms. So the top panel shows the mean square displacement of the worms in the solid media, and the dashed line, the colors are just showing increasing packing fractions. So the blue, dark blue is the highest packing fraction. And the dashed line is a comparison with simulation, the simulation for only one packing fraction, 40%. As you can see, we cannot capture the short-term dynamics because our model is very coarse-grained, is very rough, but it can somehow match the high packing fraction. What I forgot to mention, that we have also the bending stiffness and the activity parameter. How did we fix them? Because of this linear scaling with active force, the exact value of active force doesn't matter, but we use a low activity force, like F.1, because worms are not so fastly moving, they are just curling. And we match the bending stiffness by measuring bond-bond correlation of worms. So we chose a couple that matches the persistent lengths of the worms. And here you see the persistent lengths of the worms, the full symbols that are obtained by experiments in order and disordered, and the empty symbols are the one from simulation, which are we have matched the couple to match the experiments. What is interesting is that worms are a bit more complex than when we do simulation, because you see a huge change of bending persistence of worms as you change the obstacle packing fraction. In simulation, you can get an bending estimate that changes a little bit with the packing fraction, but not the way we see here, that what we see that the persistent length of the worms is increasing in disordered media with packing fraction, whereas it's decreasing with packing fraction for ordered media. And this is not a behavior we can capture by theory. It seems, at least for now, for this simple naive model, to be a biological effect that somehow they dynamically adjust their bending and stiffness. But if you use this as an input, um, so here again is the MMST of worms in the square lattice. We can, and if we can long-time diffusion, we can capture the trends. So again, the one which are going up is the worms in solid media that you can see that the long-term diffusion of active filaments is increasing with packing fraction, which is quite counterintuitive because you expect them to handle, at least in the range of semi-flexibility, we have the kappa around 10. While for the order array, it goes down with the packing fraction. So if we match the persistentness, we can explain the trends, but it's not so trivial, and it's because of these strange trends I showed you before here, that depending on what range of persistent length you have and packing fraction, you can have either of the order or disordered diffusion being higher or lower. So you can see it here. So that explains that, but nevertheless, if we match the persistent length, we can capture the trends, but not the exact values. It's because our model is too rough and we don't capture the short-time dynamics of the mean square displacement. So you need to consider some more undulations that we don't have in our model. So I would like now just to make a break and show you the worms' behavior in disordered arrays, just to see how they move. As you can see, they find their ways in this maze, and they just find these channels between disordered arrays that they move. I show it once more. It's a bit short, but nevertheless, you can see that there are moments that it goes a bit slower, and there are moments that it goes more straight, like there are moments of hopping and trapping. And again, similar to the simulation, you can look at uh, the intermittent dynamics, and in the experiments, they look at simply the speed of the center of mass of the polymer, and what they find that there are moments that it's trapped, and there are moments that it's just simply moving. So it's actually in this case for this range of activity and flexibility is more often going straight, and some of moments is trapped. And here you see the distribution of the, also they look at the distribution of the run lengths when they are going just straight in the curvilinear channels without being trapped, and how it changes with the packing fraction. And as you can see, of course, when you increase the, actually not of course, it's quite counterintuitive. When you increase the packing fraction for in disordered media, they have on the average longer run length, so distribution shifts towards higher values. Whereas in disordered media, in ordered media, it's the other way around. As you increase the packing fraction, the run length is decreasing. And if you look at the trapping time, again, the mean trapping time is decreasing for dense media in disordered, while it's increasing for the ordered with increasing packing fraction. So this is the counterintuitive part, and the way we can explain is really that the worms have a dynamic bending stiffness. Somehow they become a bit more stiff, and the stiffness helps them to go more straight, like shooting. But nevertheless, one can explain this in terms of the two contributions, the contribution of that, how long the polymer worm takes to reorient, and how long on the average it goes, what is its mean end-to-end distance. So with this, I would like to end this part and move to the part which is on active filaments in granular media. So again, this work was initiated by a bachelor student, Jena, who did a short internship project in our group. And it was so interesting that my PhD student, Mohammed, who is graduating, continued it. So we wanted to have a simple setting to mimic the granular media. So we considered a dense array of obstacles, this time the same size as the monomers. And we assume that for the first order approximation, that the the obstacles are monodispersed. The real grain, I don't think it's monodispersed, and we don't consider also friction between the obstacles. But otherwise, it's the same setting as when we had the fixed array of obstacles. The only difference is that now if the active polymer hits some obstacle, they can displace them. So, uh, of course, again, one can ask how this somehow granular matter, if you have a dense one, affects the transport of active filament. But the other question, which is more interesting, is actually how does this active filament as an intruder affect its surrounding medium? As you can see here in this picture of the real worm, they create channels and they can also compactify the soil around them. So we wanted to see how our model can uh, predict this behavior. So before I go, there is another difference with what I presented before, is that here we also consider self-avoiding polymers. We just don't have any more phantom because we assume they are really 2D objects like this picture. So we have self-avoiding, and then the phase behavior of this free space polymer changes compared to the ideal chains, because the self-avoidance at high here is again taken from the paper of Gomper, Iselholder, and collaborators, that phase behavior of active polymers with self-avoidance is different. There, what happens that if you have increased activity level and you have a low enough persistent length, at some point you induce spirals and you increase the activity further, you get very nice spirals. And actually, I have seen this in the worms in the garden by myself, but sometimes they go to a spiral, but maybe often more weak spiral because they're not so super active, the worms. So this is important to remember because I want to look now, if I put this model in the grain, what happens to this behavior of the conformation and dynamics of active polymers. And just a quick remark, when you get into a spiral, the polymer dynamics slows down dramatically, even if you have very high active force, because it's just rotating and rotating. It has a short rotational relaxation time, but the dynamics of center of mass is quite small. And before I analyze the data, let me show you a video of the active filament in the dense granular matter, again, 60%. So I'm curious what is attracting your attention in this video. Sorry, I have lost the audience view, so there are some similarities with the picture of the worm I showed you. It creates channels similar to the way worm does on the soil. But there is another interesting effect. It happens. So as it's not, I'm not seeing the audience right now. So I let it to you to think what is interesting for you in this one. So there is something happening in the medium that we will get back to it. But for now, I just let you keep it for yourself, or just if one you can tell it. And I just quickly show what's the effect of the active filament, what's the effect of granular matter on the conformation and dynamic of active filaments. So we have looked at intermediate flexibility, like kappa 10, which is similar to the value we use for the worms in the experiments in the fixed obstacles. What we find is that if you have a low activity level and mean end-to-end distance for a range of packing fraction, we look between 0.4 and 0.7, is increasing. So the polymer gets a bit more extended because of this confinement of the grains. Even though it displaces them, it creates a channel and it stays in this channel somehow. But if you have a very active filament, what happens is that the conformation is dropping a lot compared to the free space. So the black lines are the free space mean end-to-end distance. So it's dropping much quicker, and this is because of the spiral formation. And what happens is that if you have a granular matter, because it's more confined, it somehow promotes the spiral formation to the lower levels of activity compared to the free space. And that explains the shrinkage of the polymer conformation. And if you look at the dynamics, again, you see something similar in terms of the trends, that at low activities, if you have a sufficiently dense medium, like 70%, you can have enhanced dynamics, like you get beyond the free space, which is interesting, that somehow they can use the grain in their favor, and for low activity levels. And then on the high activity levels, because the polymer transitions to a spiral-like type of configuration, it gets much slower dynamics than the free space because the spiral formation happens even at lower levels of activity than the free space. But the good thing is that actually worms are not super active. They are more in this regime, so they can somehow profit from the environment to go even faster. And consider we have no friction here, so it might be a bit different in reality when you have friction with the grains. And I don't know how many of you could guess, but what was for me most amazing is when you look at what the worm does in the grain, that it creates locally some order in the grains. And we just look at the hexatic order parameter because these are just monodispersed one. And we could determine the local hexatic order parameter, which is basically you take the angle of um, the vector of two neighboring monomers with the x-axis, and for every particle you count you calculate the angle for all the neighbors, and you just look at the exponential of it. It's just basically the hexatic order parameter. And we wanted to look how this hexagonal order parameter changes over time as the active filament moves in the granular medium. And let me show you the videos here. They are color coded. So when it's yellow, you have the highest hexagonal order parameter locally, and when it's somehow this dark red is no order. So what you can see is that as the time goes by, there are more and more regions of yellow, which is regions of higher hexagonal order parameter. And it increases over time. And you can see the majority of the system starts to get ordered. Somehow the worm pushes the grains away, but then they are more, locally they get more dense. And as a result, you get higher hexagonal order parameter locally. So the video can go forever, but we stopped it here. And if you look at the local order parameter, which means that you calculate the local hexagonal order parameter for every particle, and you just take its magnitude and you sum them, what we find is that for several activity levels, at the very low activity level is the blue line, it goes up. So it seems that when active polymer moves very slowly, it has more time to adjust. So you get the highest local hexagonal order parameter at the longest time. And for the intermediate, you can also get something high, maybe a bit lower. But if it's very fast, because it goes to this spiral, you don't get much order. So I didn't show you the video, but that's interesting to know that you need somehow low to intermediate activity levels to see this ordering. And we look at the global one, which means that you just sum over all the hexagonal order parameter of all the particles before you take the average, before you take the absolute value. And this one is also increasing, but it's globally, it doesn't go that high, at least within the range of time we have measured. So it's a still open question if it can go even higher, but it's really long simulation, so it's a work in progress. So I would like to end with this with here and just make a summary of what we have learned so far. Of course, I'm looking forward to hear your feedbacks either in connection to experiments or ideas about the granular system. That the first question was how the arrangement of obstacles affects when you have fixed obstacles, the transport of the polymers. So first, I would like to emphasize that we see big differences when you have low activity levels and high packing fractions. But if you have a very highly active filament, actually it just overcomes the obstacle. It's like the moral we have as human. At some point, you can, if you put enough energy, you can overcome the obstacles. And whether the ordered or disordered obstacle enhances the diffusion or slows it down, it a lot depends on the degree of flexibility. So I'm not going to tell you which case is what because it was a bit complex, but what is important is really complex interplay between activity and degree of flexibility. For example, we saw for flexible polymer, disordered media act better. For semi-flexible polymer with a very high bending and stiffness, ordered media could really direct the motion in channels, so they led to a better channel. So these are interesting for the maybe bioengineering application that we can learn from this. And it's interesting to see also in different active filaments in real environments, how they have adapted their movement depending on the medium they are moving. From the theoretical insight, for me, what is interesting is that independent of exact details, how the medium affects the conformation and dynamics, nevertheless, you can predict the long-time diffusion of center of mass as a product of the end-to-end distance squared and the rotational relaxation time. And for grains, what we have understood so far is a work in progress, is that, as you saw, grains can induce a spiral formation at low activity levels, lower activity levels compared to the free space if you have these self-avoiding filaments. And again, here, in moderate activity levels, the dense packings can enhance transport as long as the polymers are not getting into the spiral conformation. And for me, it's at least visually very attractive that you can see that you really can, by an intruder, you can induce hexastatic aura in the granular medium. So it would be interesting to explore this a bit more. So this is a work in progress. So we are exploring the system a bit more. We hope at some point we can make these robotic worms into 2D granular matter, which is more close to the simulation setting. And of course, in reality, it's interesting to look at the effect of friction because we ignored, and also polydispersity of grains, which is the case of the real soil. And as a bigger perspective, as I told, the real active filaments in porous media, they have much more complex setting. It's 3D. There are this sort of entangled polymer network. So we hope that we can go in that direction in the future. With this, I would like to end by thanking my amazing collaborators, the PhD students in my group, and Yena, who was a bachelor student, still in 3 months, she did an impressive work. Our experimental collaborators, Rosa and Antoine, and also our collaborators, Zahra and Ehsan, who helped with the technical aspects of the simulation at the very beginning. And of course, thanks to you for staying with me, especially if you are in the time zone, which is quite late already on Friday.